In this video, we're going to talk about the topic on hypothesis testing. So what essentially is hypothesis testing? Well, in practice, instead of estimating the parameter of interest, we would like to answer questions like, is the new treatment superior than the standard treatment in saving lives? Or do older people support CY to be the chief executive of Hong Kong more? Or we would like to make a statistical decision by transforming the daily life problem to a mathematical problem. For example, a professor in biochemistry, he asked if eating boogers boosts immunity. You know the meaning of booger. Booger, actually, this is a professor. Scott Napper is a professor in biochemistry from the University of Saskatchewan in Canada. And he has a hypothesis. What if his daughter's tendency to pick her noses and eat the dry nasal mucus, they're called the boogers, actually have some health benefit? Because he suspected the nasal mucus, or what we call the boogers, actually has some sort of a microorganism or a little amount of virus inside the boogers that will trigger the immunity system of human beings. So how do we prove this theory? To confirm or to falsify this theory. Now, if we are conducting this in lecture, I would probably split the class into two groups, and one group will be eating their boogers for 1 month, and the other group without eating their boogers for 1 month, and then count the number of episodes of influenza attack between the two groups. Then that will somehow give you an insight of whether this hypothesis can be confirmed or falsified by carrying out an experiment, or what we call the clinical trials. Now, statistics actually helps to make a decision to confirm or to falsify a new theory. For example, there is a myth saying that lefties are more likely to be gifted than their peers. And there are some typical examples like Paul McCartney, like David Cameron, and Barack Obama. But whether this is true or not, because these are the biased sample from the general public, and one would have to carry out a statistical analysis by carrying out an experiment to determine what's going on. Now, statistical hypothesis testing involves decision making, and actually this is the same principle that we applied in our daily life. For example, you went to a hairstylist and told him you would like to set the hairstyle of Brad Pitt. And after he shampooed your hair, you were just too tired, and just before you fell asleep, you remember that the hairstylist was the boyfriend of the girl you were dating, but you were just too tired and you fell asleep. And by the time you woke up and your new hairstyle becomes something like this or something like that, so what would you think? And you try to be calm and analyze the case using some common sense and logical thinking. And there are only two possible choices for your decision, namely A and B. So A is, do you think A, the hairstylist did it on purpose? Or B, was it just the consequence of your unexpected movement during your sleep? Okay, so which option would you choose? Which option would you choose? You would have to gather evidence. And what kind of evidence would you have? Or which option is more likely with your information on hand? Okay, which option is more likely to be true? Did he do that on purpose, or was it just a consequence of your unexpected move during your sleep? For a fair trial, giving the benefit of doubt to the hairstylist, we assume that he did not do that deliberately. That is option B. Okay, option B. We assume that he did not do that deliberately. And with this assumption, what is the likelihood of getting this haircut? or something worse purely by chance or coincidence under the assumption of B, what is the likelihood of getting this haircut? Okay, suppose this likelihood can be quantified by a probability called the p-value. And if the p-value is 0.5, which option would you choose, A or B? Okay, so under the assumption that B is correct, that he did not do that deliberately, intentionally, the probability of getting such an haircut is very normal with a p-value of 0.5. That means there is half a chance, a probability of 1/2 that this will occur. And what if the p-value is 0.05? Which option would you choose? What if the p-value equals to 0.005? Which option would you choose? Okay, p-value equals to 0.005 means that if he did not do that intentionally, the probability of getting such a haircut or something worse is highly unlikely. But this is actually what you observed. Okay, so in general, our decision is simply based on this p-value, that a small p-value is in favor of option A, while a large p-value is in favor of option B. Now, if this probability is extremely small, if he did not do that deliberately, the probability of getting such a haircut or an even worse haircut is extremely small, which is highly unlikely. Then you would doubt whether the assumption that he did not do that deliberately will still hold true. Okay, in our daily life, decisions are generally made based on some subjective probabilities, but not for scientific research. For example, a sleep disorder specialist wants to study the effectiveness of a new herbal medicine that is postulated to increase the number of hours of sleep insomnia patients get during the night. Okay, insomnia means that which is a sickness that patients cannot fall asleep. Okay, to do so, the specialist randomly selects 12 patients and records the number of hours of sleep each gets, with and without the new herbal medicine. At a first glance, 9 patients had indicated some improvement after taking the new herbal medicine, while the other 3 indicated that there was no improvement. Do you think the new herbal medicine is effective in helping out the insomnia patients? And this is a typical hypothesis testing problem or a clinical trial analysis. To give you another example, a marketing executive of an investment company claims that they are a group of highly professional investors, that they can predict the up or down of the Hang Seng Index of the next trading day with a probability 0.8. The probability of making a correct guess equals to 0.8. That is the claim by a marketing executive. And of course, the intention is to convince someone to be their customer, okay? So that you will put a big bunch of money to the company and let them invest for you. Some information or evidence needs to be provided to make their claim more convincing. Now, that's what they claim. Is the claim justified? So they predict on the up or down of the Hang Seng Index of the next day, trading day, for each of the next n days. And there are X correct guesses out of the n independent predictions. X correct guesses out of the n independent predictions. Okay, the question is, will you be convinced if there are 4 correct guesses out of 5 independent predictions? 5 independent predictions with 4 correct guesses. That is, what if n equals to 10 and x equals to 8? 8 correct predictions out of 10 independent trials. X equals to 16 and n equals to 20. They all end up with 80%, with a point estimate of 80%. Okay? So in many situations, we're interested in testing some claims about a population parameter rather than estimating the true value of the parameter. The procedure is well known as hypothesis testing that involves the following steps. The first step is to state the hypothesis being tested or challenged, called the null hypothesis. We denote that by H naught. And state the alternative hypothesis. We denote that by H1, the alternative hypothesis, or HA, which is the one to be accepted if the null hypothesis is rejected. And the two hypotheses must be mutually exclusive, and you have to make a decision to determine which one you would accept or to retain. The second step is to collect a random sample of items from the population and compute the appropriate sample statistic. And the procedure, this is an important step, and we assume that the null hypothesis is true throughout the whole procedure and consult the sampling distribution from which the sample statistic is drawn under this assumption. And then we compute the probability that such a sample statistic or an even worse statistic could be drawn from the sampling distribution. That is, we would like to compute the p-value, And the last step is that if this probability is high, we do not reject the null hypothesis. Or if this probability is low, we reject the null hypothesis with no chance of error. Now, before we talk about the null and alternative hypothesis, we need to know how to set the appropriate null and alternative hypothesis. So let's take a look at the properties of the two hypotheses. The first one is that H0 and H1, they must be mutually exclusive, that they must have no elements in common, but they are not necessarily exhaustive. Okay, but they must have no elements in common. And two, traditional belief is normally put as the null hypothesis. Traditional belief is put as the null hypothesis, while the new concept or the new claim is generally put as the alternative hypothesis. And the fourth property is that if the null hypothesis is not rejected, usually we will just sit back and do nothing. While if the null hypothesis is rejected, that is to accept the alternative, some actions, remedies, or responses are usually needed to be taken. And more protection will be put on the null hypothesis. In other words, the null hypothesis will not be rejected, as the benefit of doubt will go to the null hypothesis, unless there is good evidence in favor of the alternative, indicating that the null hypothesis should be rejected. There is good evidence. Good evidence means a small p-value. To give you an example about the hypothesis testing, let us take a look at an example from the past examination question. And it sets from past experience the prevalence of high-risk AMI, the acute myocardial infarction subjects, which is some sort of heart disease. Okay, the prevalence of high-risk AMI subjects in the general population is reported to be p equals to 0.25. The population proportion is reported to be 0.25. Okay, now it is suspicion. This is a suspicion. It is suspected that this prevalence P is higher in city H because city H is a highly polluted city. Okay, so there is a claim that the prevalence P, the proportion of AMIs, high-risk AMI subjects in city H, is higher than the general population. So to carry out this claim, to justify this claim, a random sample of n equals to 500 adult residents of city H is drawn, of which x equals to 141 are at high risk of AMI. the question is, can one conclude that the prevalence of high-risk AMI in City H is higher than that of the general population at the 0.05 level of significance? The question is to state the null and alternative hypothesis, the name of the test statistic, the rejection region, and your conclusion clearly. Now, what we're going to do here is to state the null and alternative hypothesis first. Okay, notice that we have to find the parameter of interest in this particular question, and it is obvious that the parameter of interest is the population proportion, the prevalence of high-risk AMI subjects in the population in City H. Okay, and if you remember, the null hypothesis is the traditional belief is put as the null hypothesis, and the traditional belief is that for the general public, the proportion of high-risk AMI subjects in the population is 0.25. Okay, the general belief is that unless there is strong evidence, otherwise we would not say that City H has a higher prevalence. We can only say that City H has the same prevalence as the general population, where the proportion of high-risk AMI subjects in the general population is 0.25. But the new claim is that the alternative hypothesis, the new claim is that the P in City H is higher than that of the general population, because City H is much more highly polluted city. It's a highly polluted city. So the alternative hypothesis on the parameter is P is greater than 0.25. That is how we set up the null and alternative hypothesis. Well, based on the sample data, the sample proportion is simply X over N, where X is 141 out of 500 randomly selected subjects. P hat equals to 0.282. Okay, the sample proportion is 0.282. But the question is there enough evidence to reject the null hypothesis that the prevalence of high-risk AMI subjects in City H is greater than 0.25, is higher than that of the general public? And note that the larger is the value of P hat, the more it supports the alternative, For example, if P hat equals to 0.6, then we can almost reject the null hypothesis immediately, because 0.6 is much greater than 0.25. But how large is P hat will we reject the null hypothesis based on a random sample of size 500, and that is our main focus. Okay, now SCNC 1111 secrets. We have a secret page. What would be your reaction if I tell you that I have supernatural power? What would be your reaction? So, in order to make a decision, you would phrase it in hypothesis testing setup, and the null hypothesis is that the traditional belief would be put as the null hypothesis. Traditional belief is that Eddie wouldn't have any supernatural power unless he show us something, right? So the null hypothesis is simply Eddie is just an ordinary person, that he does not possess any supernatural power. While the alternative is the claim by Eddie that he has some supernatural power. So the alternative hypothesis is something like the null hypothesis is not true, that Eddie has some supernatural power at least. Okay, so that is the null and alternative hypothesis. So then you have the observation, and if I show you something that I can actually fly around Hong Kong, what would be your reaction? This is the observation. What would be your reaction? And your reaction would be like, okay, with an oval mouth that you cannot close your mouth. and rounded eyes. Why? You were probably very surprised to see me flying around in the lecture theater or over the campus, because under the null hypothesis, that Eddie is an ordinary man, the observation that Eddie can fly is impossible, that the observations do not agree with the traditional belief. And statistical justifications is that if the null hypothesis is true, the probability associated with such an observation or a more extreme observation is extremely small or highly unlikely. But the observation is that Eddie can actually fly. Okay, so under the null hypothesis, this probability is almost zero. Almost zero. The probability associated with such an observation is zero under the null hypothesis is true. So what would be the problem? The problem would be the assumption. There would be some problem associated with the assumption that Eddie is an ordinary man. There is no way that Eddie is an ordinary man if he can fly. Okay, so that is the rationale of carrying out a hypothesis testing. Now, going back to example 18, we need to identify the parameter of interest first. And the null hypothesis is the traditional belief, or one should be skeptical on some new claims. Okay? And hence, the predictions might not be any better than wild guesses by flipping a fair coin. That the probability of making a correct prediction on any particular trading day is 1/2. It's just like a wild guess of flipping a coin. That the Hang Seng Index will move up or down on the next day is just a wild guess with probability 1/2. So under the null hypothesis, the mathematical expression of the null hypothesis would be the probability of making a correct guess is 0.5. Okay, but the alternative hypothesis is the new claim. The claim is that the probability of making a correct guess by this group of so-called highly professional investors is 0.8. Okay, so that's how we set the null and alternative hypothesis. And now suppose that the claim is not true. That means under the null hypothesis, suppose we have n equals to 5 trials, 5 independent trading days, and the observation is 4 correct predictions out of the 5. What is more extreme? Contrary to the null hypothesis? The more extreme would be the more number of correct predictions. So the probability associated with the observations, or an even more extreme observation, is simply the probability that the number of correct predictions out of n trials is greater than or equal to that observed. In this case, when n equals to 5 and probability of x greater than or equal to 4, we can calculate this probability to be 0.1875 based on the binomial probability distribution. But the calculation of this probability would be out of the scope of this examination. But I'm just trying to give you the numbers, to figures, to let you have a taste of the p-values. So that means if out of 5 independent trials, making 4 or more correct predictions, isn't that difficult? It's not difficult, even based on wild guess under the null hypothesis. Making a correct prediction equals probability of making a correct prediction is 1/2. Then the probability of making 4 or 5 correct predictions out of 5 independent trials, you still have quite a large probability of 1.1875. That means you still have about 20% of making 4 or more correct predictions out of 5 independent trials, even though you don't have specific skews with probability of making a correct prediction equals to 0.5. But 5 out of 5, there is still a probability of about 3%. But if we increase the number of trading days to 10 and 8 out of 10, then the probability of making 8 or more correct predictions drops to about 5%. 9 or more correct predictions out of 10 will drop to 1%. And 16 out of 20, 16 or more correct predictions out of 20, the probability drops to 0.0059. And you can see how the probability is associated with X and N. Okay, for example, if you make 16 correct predictions out of 20 independent trials, and it is quite difficult to say that, well, they just make the guess at random, and these are all wild guess, because this probability is quite unlikely to take place. However, if in fact the alternative hypothesis is true, that means P equals to 0.8, then this is under the alternative hypothesis is true. The probability of making 4 correct predictions out of 5 is almost a norm. This is what we expect you to have. Okay, and 5 out of 5 is still quite high with probability of 33%, and 8 out of 10, at least 8 out of 10 correct predictions would be about like 0.6778. So you can see that if such a small probability of occurrence, 0.0059, under the assumption of P equals to 0.5 with respect to the null hypothesis. But in fact, this is something very common if the alternative hypothesis is true. So therefore, if the p-value here is small, we would expect to reject the null hypothesis and accept the alternative hypothesis with a much higher probability of occurrence. That is the rationale of the hypothesis testing procedure. Now consider the case with n equals to 10 independent trials, and x equals to 9 correct predictions. The probability of achieving such an outcome, or even worse outcome, relative to the null, that means more extreme, that is the probability of achieving such an outcome would be P probability that x equals to 9, or even worse is x greater than 9. So this associated probability is probability of x greater than or equal to 9 under the null hypothesis is true with P equals to 0.5. Remember, the stroke stands for the condition on the null hypothesis is true, where P equals to 0.5. Now this probability is 0.0107 based on the binomial probability calculation, and you don't have to know how to calculate this probability. And this is what we call the p-value. So how small is this p-value? Is it small enough to reject the null hypothesis? That is, if the null hypothesis is true, in theory, the probability of getting such an unfavorable outcome is only about 1%. That we only expect to achieve one such unfavorable outcome if we can repeat the procedure 100 times. Do you think this chance is too small? If so, such an outcome is highly unlikely under the null hypothesis. However, the group of professional investors had achieved such an outcome in just one single sample. This small p-value is calculated by assuming the null hypothesis is true, that p equals to 0.5. What if the null hypothesis is not true? Under the alternative hypothesis, this probability becomes 0.3758, which is quite common under the alternative hypothesis in achieving such an outcome. So what would be your decision? The decision is based on the p-value. On how small is a p-value would you consider as small? A commonly used value is alpha equals to 0.05, and alpha is called the probability of committing a type 1 error, or the level of significance in hypothesis testing. For a formal hypothesis testing procedure, we will fix the alpha, the level of significance, before we collect the data. And we fix alpha to be a reasonably small value and compare the p-value with alpha, with the pre-specified value alpha. The null hypothesis will be rejected if the p-value is less than alpha. And alpha is also called the level of significance. An alternative statistical approach consists of 4 essential elements, namely the null hypothesis, alternative hypothesis, a test statistic, and a rejection region. And in this example, we have the null hypothesis, p equals to 0.5 against the alternative p equals to 0.8. The test statistic is just x, the number of correct predictions out of n equals to 10 independent trading days, which is known to follow a binomial distribution with parameters n equals to 10 and p. And the rejection region, we denote this by RR equals to x greater than or equal to t. Now, the rejection region is a set, a collection of x, okay, where k is a pre-specified constant, say k equals to 8, for example. If k equals to 8, then the rejection region is that if x equals to or greater than 8, that means if x equals to 8, 9, or 10 out in an experiment out of n equals to 10 independent trading days, then we will reject the null hypothesis. Okay, RR equals to the collection of x greater than or equal to 8 means that when x equals to 8, 9, or 10, then we will reject the null hypothesis. Here, a larger value of x is in favor of the alternative hypothesis. Okay, if you go back to here, n equals to 10 and x equals to 8, under the null hypothesis, this probability is 0.0547. So the level of significance is set at 0.0547 in this particular example. If k equals to 8, then alpha, we can set the rejection region to back calculate alpha. Or somehow can we set alpha to calculate the rejection region? This is another challenge. Now this idea, the rationale or the philosophy or the concept of hypothesis testing is very much similar to a court case in a verdict. Okay, in a verdict, in a court case, the judge will have to make a decision between the null, whether to accept the null hypothesis or to accept the alternative hypothesis, where the null hypothesis is that the suspect is innocent, he had not committed the crime, and the consequence is that you have to let the suspect go if the null hypothesis is accepted. But if the null hypothesis is rejected, that means the alternative hypothesis is that the suspect has actually committed the crime and he would be plead guilty. And the consequence is that we have to send him to jail, okay, when the alternative hypothesis is accepted. Okay, so that is very similar in making a decision to choose either one between the null hypothesis and the alternative hypothesis. Now, in Hong Kong is actually practicing the common law. That means under the null hypothesis, we have to assume that the suspect is innocent throughout the trial, throughout the whole trial. And the prosecutor will have to supply more and more evidence to prove that the suspect has actually committed the crime. So in Hong Kong, in the court case, the null hypothesis is that the suspect is innocent. Just like in the hypothesis testing procedure, we will assume that the null hypothesis is true throughout the whole procedure and compute the probability of the occurrence of the evidence under the null hypothesis is true. Okay, but the fact is that the suspect had not done it, or he has actually committed the crime, and the fact is unknown to everyone except the suspect himself. Okay, so the problem is that if he had not done it, but the decision is that the suspect is innocent and we have to set him free, then this decision is appropriate. And if indeed he has committed the crime and the verdict is that he's pleaded guilty and sent him to jail, then this is also a correct decision. But if he has not done it, but the verdict is that he has actually committed the crime, then this is what we call the type 1 error. Type 1 error. Okay? Type 1 error. And this is something that we would not like to see in court. But in fact, on the other hand, if in fact the suspect had committed the crime, but he has a lot of money to hire the best lawyer in the city and to fight for this verdict, and finally he was set free, that the null hypothesis cannot be rejected only because he has a very good lawyer. And this is also another type of error that we call it type 2 error. Type 2 error means that the rejecting a type 1 error means rejecting a true null hypothesis, while the type 2 error means accepting a false null hypothesis. Okay, so basically we have two types of error. For each hypothesis testing, they exhibits two types of error as well, namely the type 1 and type 2 error. A type 1 error is made if the null hypothesis is rejected, when in fact the null hypothesis is true. While a type 2 error is made if the null hypothesis is not rejected, when in fact the alternative hypothesis is true. And we denote the probability of committing a type 1 error by alpha and the probability of committing a type 2 error by beta. And going back to example 18, we mentioned earlier that the probability of committing a type 1 error, when we set the rejection region to be x greater than or equal to 8, then the probability of committing a type 1 error, alpha, is given by 0.0547. While the probability of committing a type 2 error, that means probability of x less than 8, given that p is 0.8, is 0.3222. Okay, the probability of committing a type 2 error is quite high, but the probability of committing a type 1 error is small using this rejection region. So alpha is reasonably small but not beta. So for a fair hypothesis testing, we would like to strike a balance such that we have reasonably small type 1 and type 2 error, but somehow it's difficult to control. Now, for example, if we set the rejection region to be x greater than or equal to 9, okay, more stringent, then we have a even smaller type probability of committing a type 1 error, where alpha would become 0.0107, but beta will be inflated to be 0.6242. Okay, so you can see that exists a trade-off between the probability of committing a type 1 error and the probability of committing a type 2 error. So we have to be a little bit more careful to strike a balance between the two. The question is, can we reduce alpha and beta simultaneously at the same time? And the answer is, it is possible. By increasing the sample size, then we can reduce alpha and reduce beta simultaneously. But nevertheless, very often the alternative hypothesis does not possess a simple form that the value of P is known. For example, in example 18, the alternative hypothesis is specified by P, the probability of making a correct prediction equals to 0.8. Okay, but a composite alternative that takes the form P greater than 0.5 if the null hypothesis is rejected. Sometimes we do not want to be specific to test for P equals to 0.8. We just want to know whether this group of so-called professional investor has a higher probability than an ordinary person in making a correct prediction on the up and down of the Hang Seng Index. Okay, so sometimes we would be interested in testing the alternative hypothesis that P is only greater than 0.5. So if this is the case, then the value of beta cannot be computed. The value of the probability of committing a type 2 error cannot be computed. Not to mention the fact that we want to strike a balance between alpha and beta to make them both reasonably small. Okay, so if you may recall that we need to put more protection on the null hypothesis, because the null hypothesis is our traditional belief. We need to have sufficient evidence in order to reject the null hypothesis. To establish a new theory, we need to have sufficient evidence. Sufficient evidence means a small p-value. So therefore, we need to set alpha, the level of significance, to be small. And very often we set alpha to be 0.05 or 0.01 in general. On fixing alpha, we can determine the rejection region and reject the null hypothesis if the test statistics falls in the rejection region. Okay, so we do it the other way around. Or we can reject the null hypothesis if the p-value is less than alpha. That alpha is then the tolerance limit or the level of significance as specified before the data collection process. Okay, so the two procedures are actually identical. So alpha is determined before we actually draw the sample, and alpha equals to 0.05 is commonly used and is almost the only significance level adopted in all medical research. Now we consider example 18, a p-value equals to with x equals to 9. Probability of x greater than or equal to 9 under the null hypothesis is 0.0107. Okay, so the null hypothesis can be rejected if we set alpha to be 0.05. Okay, but the null hypothesis cannot be rejected if we set alpha equals to 0.01. Okay, because the p-value 0.0107 is greater than the level of significance, alpha. So the null hypothesis cannot be rejected. So fixing alpha equals to 0.05 in almost all medical research will avoid manipulation of the statistics to reach a more favorable outcome. That is also why I mentioned several times that the alpha needs to be determined and fixed before we actually draw the sample. Okay, let's take a look at an example. Example 19. The question says, from past experience, 60% of the patients with a certain disease recover within 3 days using the standard treatment. A new drug is developed to combat the disease, hopefully at a faster recovery rate. 100 patients are randomly selected from the population, and it is observed that 70 recover within 3 days. The question is, carry out an appropriate test to determine whether the newly developed medication is more effective at the 0.05 level of significance. More effective. The question is, how do we transform our daily life language, the language of more effective, to a mathematical notation, to transform the daily life language to a quantitative problem. And first of all, we let P be the proportion of patients recover within 3 days using the new medication. And to set the null hypothesis, unless there is strong evidence, the traditional belief would be that the new drug is equally effective as the standard drug, because we have the experience from the previous, and it is expected that the new drug would not be worse than the new drug. But before we have enough evidence, we can only claim that P, the proportion of patients who will recover within 3 days using the new drug, is equal, as effective as the standard treatment, which is 60%. And then, obviously, the alternative hypothesis is based on the claim that the new drug is more effective than the standard treatment. More effective would be the proportion of patients recover within 3 days would be greater than the 60%, would be greater than 0.6. That means the new drug is more effective than the standard drug. Now, what about the Taylor statistic? The Taylor statistic is just X, the number of patients recover within 3 days out of 100 randomly selected patients, okay? Or simply the sample proportion, X over N, P hat, okay? And by the central limit theorem, we know that P hat, the sample proportion before drawing the sample, follows approximately a normal distribution with mean P and variance P times 1 minus P over N. Okay? Now, throughout the hypothesis testing procedure, we assume that the null hypothesis is true. The null hypothesis is true. Now, the null hypothesis is true means that P equals to 0.6, and 0.6, for a more general term, we put it as P equals to P naught. P naught is the proportion as specified in the null hypothesis, where P naught equals to 0.6 in this example. So, by substituting P equals to 0.6 in this example, we know the behavior of the sample proportion, P hat, that follows, it should follow a normal distribution approximately. Under the null hypothesis, it has mean equals to 0.6 and variance 0.6 times 0.4 divided by 100, based on a random sample of size 100. And therefore, based on the observation with a sample proportion of 0.7, the p-value would be that what is the probability that we can observe a sample proportion of 0.7 or above, 0.7 or above. So by the central limit theorem, under the null hypothesis, we know that P naught equals to 0.6. Then by the Z transformation, P hat minus its mean divided by the square root of its variance. We do that to both sides, with the left-hand side being symbolically while the right-hand side being numerically. We have probability that the standard normal random variable Z greater than 2.04, okay? We have 0.7 minus 0.6 divided by 0.6 times 0.4 divided by 100. Notice that the variance term, we know exactly the value of P naught under the null hypothesis, so we will not make use of the sample proportion in hypothesis testing here. Okay, so here the probability becomes a Z greater than 2.04, and you can use the Excel to calculate this probability, equals to 0.0207. But in previous years, we do not have the Excel a software available to students during the examination. So this p-value approach will not be considered basically in this course. Okay, so but however, according to our previous introduction, with such a small p-value, if alpha is set at 0.05 and the p-value being 0.0207, the p-value is less than the pre-specified level of significance 0.05, and therefore we will reject the null hypothesis at the 0.05 level of significance. By rejecting the null hypothesis, we may conclude that the new drug is more effective than the standard treatment at the 0.05 level of significance. Okay, but we're not able to find this p-value during examination, as we will not have access to Excel, but this year we do. Okay, but you will not be required to find this probability using Excel. Example 20. Reconsider example 17. Sometimes it may not be very informative by indicating whether there is improvement in sleep hours after taking the new herbal medicine. But we should also consider the measure of improvements in terms of the number of hours sleep the patients get. And suppose the number of hours of sleep each patient gets before and after taking the new herbal medicine are given in the following table. This is for patient 1, okay? Before taking the medicine, he has 1.3 hours sleep on the average every night. But after taking the new medication, on average, he has 2.9 hours of sleep every night. And then 1.5, 3, 3.2, 3.1. And this one has no improvement at all. Okay, no improvement, but getting deteriorated. And similarly, we have 1 and 2, this patient also deteriorated, and 3 patients deteriorated out of 12, while 9 showed improvement. Okay, 9 out of 12 showed some improvement after taking the new medication. This is what we call the pair samples, that the two observations are related to each other. The two observations from the same patient are related to each other. Okay, the question is whether the new medication has will need to some improvement, whether the new medication is effective. Okay, so in this setting, first of all, we will take the difference between the pair observations by using the new medication, the number of hours of sleep ones get after taking the new medication minus that before taking the new medication. And we denote that by DI, representing the gain in the number of hours of sleep after taking the new herbal medicine. For the IVE patient, DI for the IVE patient, I equals to 1, 2, 3, up to 12. Where D is simply the number of hours sleep ones get after taking the new medication, minus that the number of hours of sleep ones get before taking the new medication. And with an assumption, we simply assume that the observations, the DIs, the gain in the number of hours sleep followed a normal distribution with mean mu and variance sigma square equals to 1.5 square, for example. This is an important assumption, and we will make this assumption for testing on the population mean mu. Okay? Now, the null hypothesis is that the new herbal medicine is again not effective. No effect. If there is no effect, if the new herbal medicine has no effect, then the gain in the number of hours of sleep for each individual patient would just be a random fluctuation around 0. Some might get higher in the next week, some may get less sleep in the next week. So it would be a random fluctuation around zero. So the null hypothesis would be that the new herbal medicine is not effective. And translated that to mathematical terms, that means mu equals to zero. The average gain is zero. While the alternative hypothesis is that the new herbal medicine is effective. Okay, that means the number of hours of sleep, the mean number of hours of sleep will be positive on the average, would be greater than zero on the average. And in the last example, I didn't do the calculation, but what you should do is you should take the differences, okay, of the 12 pairs, and then to compute the mean of the DIs. And you can do that, and just the Tay statistic, the sample mean of the differences is 1.4 and is greater than 0. But the question is whether the sample mean 1.4 is large enough to reject the null hypothesis that the new herbal medicine is not effective.